So
So
I'm going to race through highlights of our new imaging studies. Well, now they're 2 years old, actually, of of a couple of the planetary nebula NGC 6302 with HST's Wide Field Camera 3. Before I forget to mention it, Paula Moraga has a poster on the equivalent study of NGC 7027, which I'll only have a chance to say breathlessly in a couple slides from now. We also looked at that with Wide Field Camera 3. And Jesse Bublitz has a nice poster on molecular line imaging of NGC 7027. So just to give you a quick overview of the program that we proposed to HST, this represents actually the first comprehensive sets of Wide Field Camera 3 emission line images of planetary nebulae, in the sense of covering the entire waveband regime of Wide Field Camera 3 from near ultraviolet all the way out to the near infrared. And my jaw hit the floor when I looked in the archives and saw that there were just a few images from first light of Wide Field Camera 3 of 6302, and there was nothing on NGC 7027, which is surely one of our iconic planetary nebulae. So these two planetaries seem like a good starting point for doing these kinds of comprehensive imaging surveys. They're among the youngest and most rapidly evolving planetary nebulae. They both have axisymmetric and point symmetric structures, bipolar structures pretty profoundly. In the case of 6302, it's the poster child, to use Letitia's term just now, of butterfly planetary nebulae. And 7027 has every single morphology one could want in a planetary nebula. And they both have exceedingly hot central stars, and yet they have a very large masses of residual molecular gas and dust. Our motivation for this proposal, very broad brush, was just understanding the origin and evolution of bipolar structure in planetary nebulae, with the hope that these images would sit there in the archive and could be used by people well beyond our investigation. Let's see, I'm trying to advance. This is always difficult when I'm trying to do a slideshow. Okay, and I should mention that the first results paper is in Galaxies. That was the Work Plans 2 proceeding. So if you want to see the overview, it's there. And there's a version of our overview paper of 6302 that has all the details of what I'm about to tell you. Plus it'll have new details. I'm going to update it pretty soon in response to the helpful referees reports we've been seeing. So this was the overall strategy of our program. We used filters, as I mentioned, from the near ultraviolet all the way out to the near infrared. Here are their phone number like names. They go from 243 nanometers all the way out to 1.6 microns. And the science goals, again, in broad brush terms, were understanding the reach of central star photoionization, heat conduction, the spatial distributions of shocks versus photoionization, and hopefully to do some scattered light imaging. Although in the end, we learned other things from our near infrared images that we didn't expect to learn. So again, you can see the publications that are out there. If you want all the details, I'm going to be rapid fire running through these slides, I'm afraid. NGC 6302 is probably very well known to many of you, has a distance of right about 1 kiloparsec. A central star temperature that, depending on which study you look at, is between 150 and 300,000 degrees. More on the central star in a bit in the talk. The dynamical age is often quoted as about 2,200 or so years, and that's based on proper motion studies that have been done of specific knots and features in the nebula. Quite nice multi-epoch imaging studies that have been done, and we hope to use our images. In fact, Bruce will talk a little bit about that, I think, in his next talk. We're going to be using our multi-epoch images now, 10-year baseline between the two epochs of Wide Field Camera 3 imaging and some filters of NGC 6302. To be able to get more detailed view of the kinematics. And as I mentioned here, this object was the poster child for Wide Field Camera 3 first light imaging back in 2009, and that iconic image has been used over and over again in all kinds of contexts by HST and others. So here is the image gallery, a dozen images, including one I'm not showing because we didn't get good signal to noise in the 243N filter. And the amazing thing, I guess, about this planetary nebula, this is perhaps not new, but is certainly detailed for the first time in these images to an unprecedented degree. The way the character of this nebula changes depending on which filter you're looking at. There's clearly very interesting structures here that change drastically. The morphology can change drastically, in fact, depending on the filter that you look at. And the one that really pops out is the lower center panel here, the F164N iron 2 filter, where you see this S shape that was not apparent in, or at least not obvious in the previous imaging. And this nice montage was put together by co-author Bruce Ballack, who's going to talk a bit more about this nebula, as I mentioned in a second. This was, our most shocking discovery from these images, and that is this extensive set of shocks that we see in iron 2 that seems to trace an ongoing shaping of the nebula along very specific direction, lower down in the south end of the east lobe and the north end of the west lobe. You can do more with these images, of course. We have a nice span of hydrogen recombination lines from H beta all the way out to Paschen beta, 3 lines. And so we can do, I think, a better job now of seeing where the extinction due to dust lies in this nebula. Not surprisingly, it's concentrated toward the equatorial plane. And it's interesting to compare the distribution of extinction with what has been seen before. This CO image was kindly donated to us by Miguel Santander Garcia, and in their paper, they detail the structure of this molecular torus and its dynamical age and extent and so on. And you can see that what we see in the extinction map that we've been able to make, especially obvious, is the western extension of that torus in front of the western lobe. And one gets a better idea of the full extent of the torus, that it extends much farther out than is being detected actually in CO gas. The central star's detection was claimed on the basis of the first Epoch 2009 wide field camera 3 images. And when I got the first indications of our near infrared images, the preliminary images off the Space Telescope website, and started playing with them, I was very excited to see it looked like we had a more definitive detection of that central star right in the heart of the nebula. Well, wrong. It turns out that this is a foreground field star. It was here in 2009. It was here in 2019. And this is just astonishingly bad luck that the highest proper motion field star in the wide field camera 3 image field happens to be almost at the geometric center of this object. So we have hazarded a guess that the central star is actually sitting right there on the basis of these 2 bipolar cusps that you see in this multi-epoch difference image. It looks like the proper motions of those 2 features are similar, and we've gone out on a limb and made the hypothesis that we think the central star is sitting right there. Future JWST imaging is the way to go, I think, to pin down the position of the central star and more about its properties. Very quickly, this is a montage of line ratio images that we're able to make in high excitation, low excitation lines, showing the excitation structure, some of which is clearly due to photoionization, some of which appears to be due to shocks. And especially the nitrogen 2 and sulfur 2 seem to trace each other very well in this nebula. Some of that nitrogen 2 is likely due to shocks. And it's difficult to tease that out, even with these images. We're going to have to do a lot of modeling in the future to really understand fully where the shocks lie relative to the photoionization of the sulfur 2 and the nitrogen 2. Bruce is going to talk all about the azimuthal structure, I think, of this nebula in his talk. So I'm not going to say much about that, other than he generated this very wonderful schematic diagram of the different sets of azimuthal structures that you see. I'm just going to focus on 2 of these in the next slide, the clump regions. And again, these are Bruce's overlays. The clump regions show us some really interesting structure that we've interpreted in terms of nitrogen and sulfur enriched clumps that are irradiated, externally irradiated by, or internally irradiated, better way to look at it, by the central star, and are likely being wind ablated as well. And I think this is going to be, these images can be a laboratory for further studies of wind ablation and photoionization irradiation of dusty molecule-rich clumps. And we're still waiting for the ALMA data. Fingers crossed we have a priority C ALMA program to do a molecular line imaging survey of this nebula to try to detect the molecular gas that I'm almost certain is associated with these clumps, and to be able to say, thanks, Lawrence. So to be able to say something more concrete about the origin of the nitrogen and sulfur enhancements we seem to see here. So, okay, I'm going to try to run down this very quickly. We can pull together our new results from previous results from the literature and try to trace a little bit of the history of the formation of NGC 6302. It seems that dusty molecule-rich torus that defines the equatorial plane of the system was ejected at low speed, 10 kilometers per second or so, about 5,000 or so years ago, prior to the present observing epoch, that is. The torus still hides, that molecular torus still hides the star. The nitrogen-rich clumps within the bipolar lobes were then ejected in a dense but faster outflow about 3,000 years later. That's pretty well established from the proper motion studies. That the ejection of those lobe clump structures was either accompanied or perhaps closely followed by highly collimated winds from the central star system that seemed to go out along the so-called gap and amorphous azimuthal directions that were identified in Bruce's azimuthal map. And then we see these extensive iron-2 emitting shocks that are no doubt tracing an ongoing, fast, probably quite high momentum outflow from the central object or objects that exist right now in this nebula. So we've used this to try to address some of the formation scenarios that have been kicked around. I'm not going to go into this in any detail at all, just to say that in the paper, which you can read soon in the archive, the updated version of it, we talk about a couple different formation scenarios, one involving the intermediate luminosity optical transient model that Noam and Amit had put forward about 10 years ago, which explains some aspects of the model of what we see, but maybe has trouble with others. And then almost the reverse, the complementary problems exist with an onset of common envelope. But either or both of these scenarios probably work, unfortunately, or better or worse, for this nebula, and it's going to take some additional sleuthing to figure out which is the better model or the better overall model to look at, or maybe some hybrid of these two would work. And last slide, just to tell you that I'm hoping this is just the beginning of these kinds of wide field camera 3 surveys. Fingers crossed Hubble lasts a while longer. We'd like to extend the dynamical timescale out to several thousand years by looking at larger and larger, physically larger and larger bipolar nebulae. So I'll stop there and take questions. Thanks for your forbearance, Lawrence.
Thank you very much for a very nice picture, very nice results. So we do have questions. Jesus.
Hello, Joe. It was amazing images. Can you comment on the Neon 5 filter? You mentioned that this is the probably conductive layer or conductive, but my impression is that this filter is dominated by a sulfur 4 line, because at least from my simulations without thermal conduction, I cannot make this Neon 5 to shine. And yes, so because there's also no X-rays from this source, right?
Okay, that's an interesting question. There are no doubt, there must be soft X-rays that are coming from the central star, and we just can't see them because we're looking through the molecular torus. We did not detect extended X-ray emission, but our sensitivity to low surface brightness may not be that good. But I think you're probably right. I think this Neon 5 that we see here in the upper left, I think that's probably photoionized gas. Yeah, would be my guess. And so
exactly,
right. Yeah, it's interesting in the case of NGC 7027, I think there's a better case that can be made that we may be seeing Neon 5 from heat conduction. But you and I should talk about that more if it's not possible.
Yeah.
Okay, Laetitia, please.
Yes, very quickly, stunning talk. A question, you hypothesized for 6302 common envelope evolution. if I recall, this has high nitrogen, but I might be wrong. High
Yes.
nitrogen content. So
Very
that would
high.
clash with the ISAR, the common envelope evolution, where it's evolution stops and the nitrogen will never get high because there is not hot bottom burning. So maybe that would might help for your interpretation in the future. I don't know. I mean, I just want to make sure that I got the right PN.
No, I think you're right. No, the nitrogen is 10 or 20 times solar. Nitrogen to nitrogen to oxygen, I think. I think I have that right. It might be nitrogen to hydrogen. Sorry, it's 10 to 20 times solar.
Similar,
based on other
similar.
studies. Yes, yeah. No, you're right. And so that's an interesting point. Thank you. Yeah.
Okay, Ravindra?
Yeah, maybe sort of a related question to what Leticia was just saying. When you said nitrogen sulfur-rich enhanced abundances, enhanced relative to what? To what you would expect for the abundances for AGB star, the progenitor AGB star, or
relative to solar.
Relative to solar. But would
Yes.
you? I mean, this is what are those type 2 PN within? Would you
Yes.
expect that nitrogen to be
Right.
enhanced anyways?
Right. It's
So-
not, I think in that sense, it's not surprising. And so maybe it goes to Leticia's comment as to it might be telling us more about the AGB star progenitor, right?
And what about the sulfur enhancement? Is that expected also for the same reason that the nitrogen enhanced? I don't think so, right?
That's a good question, and it's outside my comfort zone. So if anyone wants to address that, I'd love it.
I guess what my question is, I thought when you said nitrogen sulfur enhanced, you were meaning that they were shining brightly in these filters rather than saying that the abundances were higher. So could you clarify?
I think it's both. I think that certainly that, and I'm less confident about the sulfur, but certainly the nitrogen to hydrogen, I think. And I'm piggybacking on published results for nitrogen to oxygen and nitrogen to hydrogen in this nebula, and using those results and my measurements of nitrogen to H alpha to say that those clumps are extra nitrogen enhanced.
Okay, thanks.
Okay, so not to run late, and we're gonna take more questions. So we have Martin and Miguel after that. Martin?
Yes, a beautiful data set, Joel.
Well, thank you.
I'd like to ask you whether you have some kinematical information on those ablated flows, and what kind of information can you obtain from this?
We have some very nice kinematic information on the basis of our images in the common filters with respect to the 2009 images, and it's very complicated and quite a mess in many ways. But the bottom line is the studies that were done by Meeburn and by a name I can't pronounce that used two epoch HST images, those hold up for the clump regions. Those are about 2,200 years or so in dynamical age, but then there are much younger structures near the center of the object. So it's clear that there's been a lot going on over the last 2,000 years.
Okay, thank you.
I hope we do more. We can tell you more very soon about that.
Okay, Miguel?
Beautiful talk, Joel. Thanks. My question is on the iron 2 emission, which seems quite asymmetrical. Do you have a view on why would that be? Maybe a projection effect?
Well, yeah, partly projection effect. I think it's also precession. Question mark? Perhaps. Yeah. Well, all I can tell you is when Adam Frank, who's co-author in the paper, looked at the image, he said, "What's going on there?" And I Adam, you need to tell me.
Yeah, in some ways it reminds of the lighthouse of M29, but that's probably jumping to conclusions.
Well, it seems like it must be a longer-lived phenomenon, perhaps, because of the extent of these shocks. But yeah, it's very confusing.
Thanks.
Okay, So the last question will be with Stavros, and then if you have any other question, please go to the Slack. So Stavros, a quick question.
Yeah, quick question. Thank you. Hi, Joel. My
Stavros.
question is, this iron emission, is it certain that comes from shocks, or it can be possible from photoionization? How do you distinguish these two processes?
You know, I think it's the excitation that's required to get to the upper level of that iron 2, you know, singly ionized iron state. And I'd have to go back to the literature and remind myself what the details are. But there's a pretty well-established line of literature going back that says that, you know, iron 2 is due to shocks. I think it's really worth revisiting that, perhaps. But in this case, it seems pretty clear cut. I think if it were photoionization, you would think that you would see it where the sulfur 2 and nitrogen 2 are, for example, and we don't. At least not as bright.
Thank you.
Sure.
Okay, so thank you. So if you have more questions, please put them in the Slack so we can keep track of them. And thank you again, for a very interesting talk.